Decoding the Chip, a deep dive into semiconductor technology. Welcome to Learn Skill Daily. Curious about the technology powering our modern world? You're in the right place. In this video, we'll explore the semiconductor industry, its history, manufacturing processes, key players, and future innovations. Before we dive in, don't forget to like, subscribe, and comment below. Your support helps us bring you more exciting content. The role of semiconductors. Semiconductors are the unseen engines driving modern technology, from smartphones and computers to cars and medical devices. These tiny chips power the devices that shape our daily lives. Without them, high-speed internet, AI, and advanced computing wouldn't exist. They're everywhere, integral to household appliances, entertainment systems, and even life-saving medical equipment, quietly enhancing our quality of life and driving innovation across industries. Why it matters. The semiconductor industry is a global enterprise and a testament to human ingenuity. Companies and nations collaborate and compete to push the boundaries of technology, enabling breakthroughs that transform how we live and connect. What's ahead? In this video, we'll uncover the history and evolution of semiconductors, how chips are made from sand to circuits, the companies shaping this industry's future, emerging technologies redefining what's possible. Let's dive in and explore the remarkable world of semiconductors, the backbone of our digital era and the key to tomorrow's innovations. The roots of the semiconductor industry trace back to the early 1900s with the discovery of silicon and germanium, materials exhibiting unique electrical properties. These discoveries laid the foundation for technologies like crystal radios, which were among the first semiconductor-based devices. In 1947, the invention of the transistor by John Bardeen, Walter Brattain, and William Shockley at Bell Labs marked a revolutionary leap. By replacing vacuum tubes, transistors enabled smaller, faster, and more reliable electronics. The next leap came with the invention of the integrated circuit, IC, in the late 1950s, credited to Jack Kilby, Texas Instruments, and Robert Noyce, Fairchild Semiconductor. ICs integrated multiple transistors onto a single chip, enabling exponential growth in functionality and complexity. The rise of Silicon Valley in the 1960s and 1970s was fueled by semiconductor pioneers like Fairchild Semiconductor. Their innovations laid the groundwork for companies like Intel and AMD, which pushed computing power into the mainstream. By the late 20th century, the industry became a global enterprise, with key players emerging in Japan, Taiwan, South Korea, and China. This globalization reshaped the competitive landscape, creating the complex ecosystem we see today. This revolutionary invention, utilizing semiconductor materials like germanium and silicon, could amplify and switch electronic signals in a much smaller and more efficient package. The transistor's ability to perform these functions with greater reliability and less power consumption marked a significant leap forward. The invention of the transistor marked a turning point in the history of electronics. It not only improved the performance of existing devices, but also opened up new possibilities for innovation and miniaturization. It paved the way for the development of integrated circuits, commonly known as microchips, in the late 1950s. These microchips were able to integrate multiple transistors and other components into a single compact unit. ICs combined multiple transistors and other electronic components onto a single silicon wafer, significantly increasing processing power while reducing size and cost. This innovation was crucial in the evolution of modern computing and electronics. This breakthrough led to the birth of the modern semiconductor industry, with companies like Texas Instruments, Fairchild Semiconductor, and Intel emerging as pioneers in the field. These companies played a pivotal role in advancing semiconductor technology and making it accessible to the masses. These companies drove forward the miniaturization trend, packing more and more transistors onto a single chip, leading to the exponential growth in computing power that we have witnessed over the past few decades. This relentless progress has enabled the development of everything from personal computers to smartphones, revolutionizing the way we interact with technology. The process of transforming raw silicon into a complex semiconductor chip is a marvel of modern engineering, involving hundreds of precisely controlled steps. Silicon wafer manufacturing. Wafer preparation. Source: High-purity silicon is extracted from silicon dioxide, sand, and refined. Crystal growth. The purified silicon is melted and then slowly solidified into a large, single crystal ingot using the Czochralski process. This process is crucial for controlling the crystal structure, which directly impacts the performance of the final chip. Wafer slicing. The ingot is carefully sliced into thin circular wafers, typically around 300 mm in diameter. Polishing. The wafer surfaces undergo rigorous mechanical and chemical polishing to achieve a perfectly smooth and mirror-like finish. This is essential for subsequent processing steps and ensures consistent film deposition. Key players: Shin-Etsu Chemical, Japan; Sumco, Japan. Deposition. Purpose: to add thin layers of various materials, for example silicon dioxide, silicon nitride metals, onto the wafer surface. These layers form the foundation for the active and passive components of the integrated circuit. Methods: chemical vapor deposition, CVD. Chemical reactions within a chamber produce the desired material, which then deposits onto the wafer surface. Examples: Applied Materials, USA; Tokyo Electron, Japan; physical vapor deposition, PVD. Materials are vaporized, for example, by evaporation or sputtering, and then deposited onto the wafer. Examples: Lam Research, USA; Ulvac, Japan. Atomic layer deposition, ALD, allows for the extremely precise deposition of atomic-level thin films, crucial for advanced node manufacturing. Examples: Veeco Instruments, USA; Cambridge Nanotech, USA. Photolithography. Purpose: to transfer intricate patterns from a design blueprint called a mask or reticle onto the wafer surface. Process: photoresist coating. The wafer is coated with a light-sensitive material called photoresist. Pattern exposure. The wafer is exposed to light, typically UV or EUV, through the mask, selectively exposing the photoresist. Development. The exposed photoresist is developed, leaving behind the desired pattern on the wafer. Key players: ASML, Netherlands, a leading supplier of EUV lithography systems; Canon, Japan; Nikon, Japan. Etching. Purpose: to remove unwanted portions of the wafer to create the 3D structures that form the transistors and other components. Methods: wet etching uses chemicals to dissolve specific materials. Dry etching employs plasma to achieve highly anisotropic etching, resulting in precise vertical features. Examples: Lam Research, USA; Tokyo Electron, Japan. Ion implantation. Purpose: to introduce dopant atoms, for example boron, phosphorus, arsenic, into specific regions of the silicon. This process alters the electrical conductivity of the silicon, creating P-type and N-type regions that are essential for transistor operation. Key players: Axcelis Technologies, USA; Applied Materials, USA. Metallization. Purpose: to create the interconnections that link the various components on the chip. Process: deposition of conductive metal layers, typically copper. Patterning of the metal layers to form the desired connections. Chemical mechanical polishing, CMP, to planarize the surface and remove any excess metal. Key players: Applied Materials, USA; Lam Research, USA. Packaging. Purpose: to protect the chip from environmental damage, provide mechanical support, and facilitate electrical connections to the outside world. Process: dicing. The wafer is diced into individual chips. Dies. Die attach. The chips are attached to a substrate, for example ceramic, plastic. Wire bonding. Fine wires are used to connect the chip's internal circuitry to the external pins. Encapsulation. The chip is encapsulated in a protective package, for example plastic, ceramic. Key players: Amkor Technology, USA; AC Group, Taiwan. Testing. Purpose: to ensure that each chip meets the required specifications for performance and reliability. Process: rigorous electrical testing is performed at various stages of the manufacturing process. Key players: Advantest, Japan; Teradyne, USA. After the fabrication process is complete, the wafer is diced into individual chips, each containing millions or even billions of transistors. Don't forget to support us. If you've enjoyed this exploration of the semiconductor industry, please give this video a thumbs up, subscribe to Learn Skill Daily, and let us know in the comments which part you found most fascinating. Your support helps us bring you more exciting content. The semiconductor industry is a vast and intricate global ecosystem, with a diverse range of companies contributing to the research, design, manufacturing, and distribution of these essential components. These companies are spread across different continents, each playing a unique role in the supply chain, ensuring the seamless production and innovation of semiconductor technology. Some of the key players in this industry have played pivotal roles in shaping its evolution and driving technological advancements. Their contributions have not only advanced the industry, but have also had a profound impact on various sectors, including consumer electronics, automotive, healthcare, and telecommunications. Intel, founded in 1968, is a household name in the semiconductor industry, renowned for its microprocessors that power a vast majority of personal computers worldwide. United States Intel pioneers in microprocessors and IDM innovation. Applied Materials, leader in equipment for deposition and etching. Lam Research specializes in plasma etching and deposition. The company's relentless pursuit of Moore's law, the observation that the number of transistors on a chip doubles approximately every 2 years, has been a driving force behind the exponential growth in computing power. Taiwan, TSMC, dominates with cutting-edge nodes like 3 nanometers. Japan, Tokyo Electron, supplies etching and deposition tools. Canon, Nikon, leaders in lithography. Samsung, a South Korean electronics giant, is another dominant player in the industry, known for its memory chips, which are essential for storing data in electronic devices. Samsung's memory solutions are integral to a wide range of products, from smartphones and laptops to servers and data centers. Samsung is also a leading manufacturer of smartphones, televisions, and other consumer electronics, giving it a unique advantage in the industry. By integrating its semiconductor technology into its consumer products, Samsung can optimize performance and efficiency, creating a seamless user experience. Taiwan Semiconductor Manufacturing Company, or TSMC, based in Taiwan, is the world's largest dedicated semiconductor foundry. TSMC's business model focuses on manufacturing chips for other companies, allowing it to specialize in high-volume production and advanced process technologies. China, SMIC, expanding into advanced chip manufacturing. Netherlands, ASML, sole supplier of EUV lithography systems, essential for advanced nodes, emerging trends and future directions. The semiconductor industry is evolving rapidly, driven by both opportunities and challenges. New technologies. Quantum computing promises unparalleled processing power. Neuromorphic chips mimic the human brain for efficient AI applications. Globalization and geopolitics. Governments worldwide are investing heavily to secure domestic chip production. Initiatives like the US CHIPS Act and the EU CHIPS Act aim to boost regional manufacturing. Environmental sustainability companies are adopting water recycling, energy-efficient fabs, and other green practices. Emerging players, startups in Silicon Valley are developing innovative AI accelerators and photonic chips. Conclusion: the semiconductor industry is the lifeblood of modern technology, enabling advances in AI, healthcare, autonomous vehicles, and beyond. Its history is a testament to human ingenuity, and its future holds even greater promise as it pushes the boundaries of innovation. Stay tuned for more insightful content on Learn Skill Daily, where we break down complex topics to help you stay ahead in a rapidly evolving world. See you in the next video.